It keeps going on down.
I've got a big enough mouth. I can probably.
You can probably listen. Okay. Okay. Good afternoon. Hope you all had a good lunch, as I had. Ooh, Lisa.
She can come up.
Yeah. So the afternoon session, the first session of the afternoon, we are going to talk about the accuracy and the sensitivity of this tool set, the technology that you have been hearing since this morning. As you know, there is lots of interesting things that you heard this morning, and this is really going to help you to put it on the square, whether how much of this information is believable and how much of them are really useful. So that's what our speakers this afternoon is going to talk about. Actually, first, Don is going to talk about the source tracking accuracy and the study design. Don, would you mind introducing yourself and talk about it?
Great, thank you. Thanks. I guess just a couple of semi-serious things to say, because nothing's ever completely serious. I'll try to keep you out of the post-lunch stupor. I know it's going to be hard, but we'll try to get it out now, and then everything will be cool for the rest of the session. Second, I wasn't invited to give 2 talks today, so I apologize that I ended up giving this morning's talk, and then you have to listen to me again so soon. It's just the way it shook out. Jorge Santo Domingo, whose name I can't pronounce nearly as well as Sally did, was unable to attend, so it was my pleasure to stand here in his place and try to give a perspective on history and current directions. Third, this talk is going to be a little bit Stoeckel-centric. I apologize. Those are the materials that I had available to me. I want to recognize that lots of other people in the room have done a lot of similar work. Each one of the studies that we go through in this section is meant to not be a case study and not be an advertisement of the type of work that I have done in my research career. But these are collaborative designs, if you want to put it that way. When you're trying to decide how do you want to design your next experiment, the best thing to do is to go to a conference like this with Jody and Sadowski and George and Chuck and buy a pitcher of beer and talk to those guys about how to design your next experiment. And so I will talk about, and I'll give as examples, the results that we collected in my study group, but recognize that these ideas are a combination of ideas from multiple researchers, the top quality researchers in this field. So these ideas ain't mine. What do we want? Collaborators? Most of this work was done while I was at the U.S. Geological Survey. I'm now at Battelle Memorial Institute, which is a not-for-profit research institute out of Columbus, Ohio, worldwide organization that does investigations in everything, including environmental issues. USGS was my salary, and also a lot of internal support. Ohio State, Orsenko, CDPHE, US EPA were all valuable collaborators in the various research pieces that we'll discuss. We alluded to this a couple of times today, that one of the most valuable things you can do in microbial source tracking research is define your question. So I'm going to limit the conversation, or at least my part of the conversation, to this particular question. I want to measure E. coli and source tracking markers in X location and determine where did an increase in E. coli correspond with an increase in MST markers. Without the upstream-downstream evaluation, it's very difficult to say, yeah, my E. coli came from this source. So I'm limiting to human, non-human, before and after, and relationship. Can the markers be used to evaluate, did this increase, did this shift from expectation, can that be explained by a contribution from sources? So I won't apologize for it anymore. That's my paradigm. That's what we'll try to do. I think those are answerable questions with modern microbial source tracking capabilities. Things that I'm going to pound on, things that I think that are very important if you're going to try to do this. You have to be quantitative, and in order to be quantitative with microbial source tracking markers, you have to have an internal spiking recovery control so that you know that you collected Even if you don't know that you collected 100% of the DNA from that sample, you know what proportion of it so that you can back calculate, you can normalize. If you collected 10% of the DNA in one sample and 90% of the DNA in another sample, well, no wonder you found 10 times as much fecal contamination in one as the other. So there has to be some control of your extraction. Sorry, I got ahead of myself. I got all excited for a second there. You have to understand your markers. Confirm the sensitivity and specificity of your marker to know that what you're measuring is actually fecal contamination from that particular source. Depending on what you're doing, you might need to understand seasonal variability. You might also need to understand, and I guess I already defined my objective. To meet my objective, you have to know the relation between the marker, in my case bacteroidales-based markers, and the E. coli content. Confirmation of that you don't have differential die-off. We've already talked about that. Differential die-off, differential survival, depending on if you're a half-empty, half-full person, right, Jody? Positive control tests to say, well, this is my theory. I say that this is the correct interpretation of my results. Can I prove it in an environmental setting to answer people like me when I say, well, are you sure? And then some techniques to limit false positive interpretation. So we're going to try to go through all that in about 14 minutes. Not really. Spike and recovery. There's a paper that was published, Water Research 2009. Linda Dick was a collaborator at Ohio State. We correlated, in this case, a plasmid, DS red. So we spiked in a plasmid, a known quantity of plasmid, into the fecal slurry or the water sample prior to extraction. We recovered it. You'll notice these recovery rates are not exceptional. Our recovery rates were quite low. We did another experiment where our recovery rates were about 60%. We were able to use those recovery proportions to back calculate, to back normalize, and account for recovery efficiency in our results. I'm really not going to try to explain to you the experimental design and results and interpretations. I just want to show you examples of how these things have been done. Not to say this is the way to do it. It's just examples of how these things were done. And if most of you, I suspect, are not going to be the actual analysts, many of you will be the people who are paying for the analysis. These are things you can ask for. These are things that you can ask educated questions about, informed evaluations of. Are you happy with the analysis that somebody is doing? Apologies to the people who are doing the work. Sensitivity and specificity. With Orsenko and Ohio State, we collected sewage from 5 treatment plants. We collected feces from other animals at some locations. We did it quarterly to evaluate for seasonal effects. We analyzed for fecal indicators and MST markers. Human marker, as Jody says, I normalized to per gram dry weight fecal material. It's a gross thing. You know, anybody baked human sewage in their drying oven before? Fantastic. E. coli ranges from, on a log scale, 10 to the 6.7 to 10 to the 8th. Allback is ranging about 10 to the 10th, 10 to the 11th. QHF 183 is one of the human markers. Also ranges from 2 orders of magnitude. These things are ranging by a factor of 100 when they're normalized to a per gram dry weight, to a solids content of fecal material. Vacuum, similarly, between 8 and 10. The birds, the pets, the rodents, ruminants, deer, specific deer ruminants, we also have E. coli concentrations. We also have allback. We do not expect to find these 2 markers in those sources, but we did. Dogs, we can talk more if you'd like about dogs. If you've been on a farm, you know about dogs. So dogs will eat anything. Dogs have a lot of things in their guts. What was a little surprising was this cow, but this was very close to the limit of detection. I can't rule out the possibility that it was in-house cross-contamination. These guys, though, are sitting up at 6.5 to 7 as opposed to 5.5. So there are 10 times the limit of detection. What's valuable to notice is that although these are false positives, they're so far below the content of human sewage. And that gets to the issues of quantification, because I think that you can exclude them as sources, even if they are the source of a false positive. It would take so many tons of cow shit to put that much QHF80, to put that much E. coli in, that you can exclude that as a source. Harwood?
Are those on a log scale?
Yeah.
Okay. I'm just being confused.
Okay, yeah, sorry.
I don't see it on your slides. So.
Yeah,
That's all I'm saying.
Yeah, you're right. I do say copies per gram dry weight. Yeah, it's log base 10 copies per gram dry weight. Thanks, Harwood. One thing that makes us wonder, well, how are we going to correlate the markers with E. coli is this plot. An R-square of 0.01 ain't great. What is great is that this box has bounds. So although it doesn't go all the way down to 3, and it doesn't go all the way up to 14, there are limits. And so an approach that I've espoused that I'm not going to go into, because that's not the point of this talk, but it's used as an example, is if you can't use the average, go ahead and use the ratio from minimum to maximum as the maximum amount that you could possibly have from that source. And if your marker concentration multiplied by that ratio, I'm going too far here. If your marker concentration multiplied by that ratio comes up with a very small amount of E. coli, even if you're maximizing how much E. coli, the ratio, even if you're maximizing, if you're still only putting in 100 E. coli, well, you know that there's not more than 100 E. coli from that source in there. We can talk about that another time, or you can read the articles. The point of this was that if you don't understand the sensitivity and specificity of your marker, you're not going to be able to make good interpretations. I'm sorry to jump around, it's right after lunch. And that there is not necessarily a good direct correlation between marker concentration and E. coli concentration. So the use of a simple ratio may not be entirely effective. And you wouldn't know that if you hadn't tested it, right? Stability. Going back to Jody's issue of differential die-off or differential survival in the environment. Another article, again with, this is just with OSU, but Orsenko helped to pay for it. We collected water out of the Olentangy River at Ohio State's docks. We put them in incubators. We seeded them with a not unrealistic amount of sewage. I mean, you have to put in enough to detect, and we wanted to be able to detect several orders of magnitude, but we made sure that, I think it was 30 milliliters of raw sewage in each of those carboys. So it's less than a percent sewage. So we're still dealing with river water. And we measured over time. Some of them were cold, some of them were warm, some of them had ultraviolet irradiation, some of them had the presence of sediments. We wanted to see whether, if we were going to apply a ratio-based analysis, is the ratio going to hold regardless of the age of the fecal material? And this goes back to the lessons learned from fecal coliform fecal strep ratio. 5 conditions, 4 time steps. We went up to a week and a half. We wanted to see the consistency of those relations between human marker and E. coli. The human markers decayed more rapidly than did the E. coli. So if we, in the interpretations, we proposed that we use the ratio, that we use our analysis, not to say there is human fecal contamination in here and how much human fecal contamination, but rather there's some utility to saying there's no freaking way there's substantial amount of human contamination in this sample. So if you're turning the analysis on its head and you're saying, I want to exclude sources of fecal contamination from this waterway, we had a discussion at lunch about if you have a background level of contamination, fecal contamination in a stream coming from wildlife, and you want to argue that it's not a controllable source, you should not be coming down on the cattlemen, you should not be coming down on the cities, you should not be coming down on the septic systems. Well, one way to do that is to demonstrate realistically that the contamination, the fecal contamination, didn't come from humans and it didn't come from cattle. And if you're going to follow that approach, then having the E. coli decay more rapidly, or the marker decay more rapidly than E. coli helps you. It just makes it more conservative mathematically. All back decayed much more slowly than E. coli. Here are some of the plots. Allback is decaying more slowly. The markers in general are decaying, and we're running into detection limit issues down here. But we have reasonable correspondence between the markers, the human-specific markers, and the E. coli. Allback, well, there seemed to be a sediment-associated group of allback marker. Semi-quantitative interpretation. This is what I was getting at a little bit earlier. This comes from the paper I wrote with Jody, not so long ago it seems, but maybe it is a bit ago, that why do you need to quantify? The reason to quantify is because you may have false positive indications because you don't have perfect sensitivity. The other reason is this plot I showed earlier. If you don't quantify, you might come up with a false indication that a source is an important source when in fact it's there, it's contaminating, but it may not be contaminating at a level that's relevant to the regulation. If you're only contaminating at a level of 82 CFU, that's below any of the standards. You don't want to implicate human sources in that case. So there are people who try to use presence-absence and say, well, because of the pattern of presence-absence responses, because of the pattern of presence, I feel like we can say that there's X chance that human sources were important. If you have more presence if you have a higher frequency of detection in one watershed compared to another watershed, the argument would go that you have a higher concentration, you have more contamination from that source in one watershed from another. If you go through the math, though, and I won't bore you with any of with the example, but in order to make that analysis mathematically, you have to know what the size of the contributing populations is. In order to prove that idea that more detections means more contamination from that source, you have to know what the size and you have to know the sensitivity and specificity. If you know those things, if you know the size of the contributing populations, you don't need to know microbial source tracking. So I do not believe, looking at the work that other people have published on presence-absence distributions and trying to do the statistical analysis of presence-absence distributions to come up with a qualitative idea of who's contributing, it doesn't hold water because in order to solve the equation, you have to know more about the system. Using the ratio, the mass balance equation, this basic chemistry dilutions. E. coli in the feces divided by E. coli, or divided by marker in the feces equals E. coli in the water divided by marker in the water. If you dilute fecal material in water, if you make poop soup, this relation should hold, right? You're diluting them both 10 to 1. When we rearrange it, you can say that the E. coli in the water that comes from a source equals the amount of water that's associated with that, the amount of marker that's associated with that source times the ratio. If you're using the average ratio, you might be wrong because of the range of values. So what a simplistic way that we tested, it's very simplistic. There's plenty of room for enhancement of this and doing it better. But a simple way to do it is to say, okay, use the 90th percentile of E. coli and the 10th percentile of marker. You're maximizing it. You're saying, in English, what you're saying is, what is the highest level of E. coli that could possibly be attributed to this source based on the range of marker concentration and E. coli concentration that we detected in our positive controls? Oh, thought I had more about that. I suppose I do. So that's an idea that is not the point of this evaluation. The point of this talk is to say, well, how do you validate that idea? How do you show that, yeah, you have this idea, it may or may not be true. How are you going to validate it? We made a series of soup samples, some of which had cat and humans, one of which had cattle, one had horse, one had human. Using the QHF 183 and vacuum, we detected human in the mixture of cat and human. We did not detect human in the cattle and horse ones, and we did detect human at a relatively low level, 900 E. coli, just a multiple of a couple of times beyond the regulatory limits. Using Bowback for cattle, and that's where we were talking about Bowback earlier. We did detect Bowback in the cat and human because we detected Bowback in the cat samples. It's a marker that does not have perfect specificity. We detected Bowback in the cattle sample, not in the horse, not in the human. So presence absence, we detected that we had perfect positives, but we had we had perfect negatives, but our positives, we had a false positive. The next thing we wanted to do was to see, can we tell the difference between a lot and a little? So using the approach, using the approach that we showed in the equation slide, the estimated number of E. coli, we calculated how much E. coli we added. We think we added 810 human, 620,000 from cats. We think we added 42,000 from ruminants. We did this by, what's the mass of feces we put in, what's the concentration of E. coli in the feces, what do we think we added? It doesn't always add up. It's an imperfect science, this detection of E. coli, but within reason. The upper limit that could have come from humans was 62,000. What we think came from humans was 810. Because of, because that Bowback marker was detected in that sample, it came from cats it turned out, but it was detected in that sample, it's possible that if there had been ruminant contamination, it would have contributed up to 67,000 E. coli. So this is a case where our validation said, you know what, nice try, but it didn't work out all that well for you. You got a true positive, but you also got a false positive. What's nicer is, in this case, we're saying there was no detection of the human marker. The ruminant could have put in up to 350,000. It was actually 42,000 or 24,000. The actual measurement was 24,000. We threw in, what was this one? This was horse. We didn't detect any of the markers, so we know that that sample didn't have human or ruminant or cattle in it, ruminant in it. The QC blind, where it was a very small amount of human, we detected the human, we did not detect the ruminant, so we were able to, the upper bound held true in those cases. Can we use it in an environmental setting? Poop soup is relatively easy to analyze and draw interpretations from. Can we do it in a real world study? We went to a beautiful area of on the border of West Virginia and Kentucky, where someone had the foresight to build a waste treatment, or I'm sorry, a waste collection system, but failed to build the waste treatment system. We floated downstream until our curiosity was satisfied. We didn't even get to the town. So we took samples from the river at point A, B, C, and D. There's a very small package plant here. There is a very big creek of sewage right here. We had low concentrations of E. coli at site A. They went up at site B. At site C, they went up further. In site D, they went not nearly as much as I would have expected from the size of this sanitary discharge, but they did go up. So the question was, can we attribute that increase in E. coli to human sources in a case where we know it's human sources? We don't know the age of it, but we know it's a human source, and we know it, and it's in an environmental waterway. The small package plant was a trickle. The river of sewage, you don't need a fluorometer to see the optical brighteners in this one. It's about 3 feet wide and a foot deep. That's a chair where people would fish there, partly because it was easy access, and boy, those fish were big. Proof of concept. Our measured E. coli being these values, our maximum potential from human being these values, we indicated that humans were a reasonable hypothesis. We could not reject the hypothesis that humans contributed in this setting. We did a larger scale on the Ohio River at Cincinnati. The Little Miami River is known to have a lot of combined sewer overflows. We went on it only rained about 0.2 of an inch, but it was enough to trigger an overflow in that system. So the E. coli concentrations that were measured were 15, 5, 29, 2,000, 200, 212. So we did have a combined overflow in the Little Miami River. It jacked the E. coli concentration up to close to 3,000, and downstream, even as far down as River Mile 470, so 6 miles downstream, we're still seeing the effects of this combined sewer overflow. We were playing with different ways to do the equation that I showed you earlier. In each case, the human source was not discounted because, well, we believe there's a human source there. So again, we don't prove things, we failed to disprove things. We failed to disprove that the human source contributed. We know that human sources were there, so we saw that as a success. So these are examples of small scale, large scale, how you can do a field validation of an idea of how to do quantitative microbial source tracking. We then floated from Pittsburgh down to the beautiful town of Pomeroy, Ohio, and went through some really awesome river towns, collecting water samples kind of when we wanted to. It was plotted out when we would collect the water samples. We were bracketing areas where we did not expect human sources and bracketing areas where we did expect human sources. Wheeling is known to have combined sewer overflows. Pittsburgh is Pittsburgh. Marietta, we were expecting some CSOs, but in these regions, we weren't expecting any human sources. So we were doing both positives and negatives there. We found that left descending bank, mile 3.3. We found that as we bracketed reaches on the left bank, right bank, and center, we were finding these dramatic increases of E. coli at certain points. In many cases, we could go to the US EPA's websites at the discharges, we could look at fine histories and say, yeah, well, there's a combined sewer overflow there. Yeah, those guys don't even have secondary treatment on their wastewater treatment plant. One of them was a little bit puzzling, and that was downstream from Weirton. We looked at that map 4 times because I thought Steubenville was going to be putting out the sewage. Steubenville's a decent-sized town, and no offense to the guy who runs the waste treatment plant, it's underfunded, it's a little rickety. We expected that there would be times when the Steubenville waste treatment plant was doing an inadequate job. But the contamination wasn't on the Steubenville side, it was on the Weirton side. Weirton's not much of a town, it's a little tiny town. So that was, most of them we could explain by patterns of human populations and known characteristics of the waste treatment plant. A year later, there's a news article that Weirton has been emptying raw sewage into the Ohio River for 50 years. So the lesson there is serendipity and keeping your eyes open for external sources of information that are going to help you explain your findings. Sometimes the best laid plans do not bear fruit, but you get lucky. So my comments on study design, and I hope this is something that's been useful and moderately entertaining and not a waste of your post-lunch time. We have to understand the source identifier. In order to interpret the patterns of detections, you have to know what your source identifier is acting like. Bowback is found in multiple sources. So you have, in a tool, especially in a toolbox approach, what many people do is they try to do the balance between a very specific a very specific marker that has a low sensitivity. You may have false negatives, but you never have false positives. And you may, and the trade-off is with one that has a high sensitivity but poor specificity. You may have some false positives, but you never have false negatives. And in a toolbox approach where those two hit, well, then you've got a much greater assurance of a true positive. Challenge the assumptions. Challenge the assumptions of, think about what the assumptions are you making in order to interpret your data. And it doesn't have to be done by each researcher. Look in the literature, but evaluate whether you have differential die-off. Figure out whether or not alternate explanations exist and have those alternate explanations such as differential die-off, such as an imperfect relation between the fecal indicator bacterium and the marker concentration. Could those alternate explanations also factor in, and can you discount those to support your main hypothesis, what you're trying to show? We already talked about those. Quality of data, the internal controls, the spike in recovery in order to get quantitative, quantitative PCR doesn't mean jack if you don't have quantitative recovery of your DNA. Good laboratory practices, we did not go into this. I think Oren will in the later talk. But we can't discount that, but that's been written about and discussed so much that we're talking about amplification controls to test against matrix inhibition. We're talking about quantification controls. False negatives require a no template control. That's more for the laboratory practitioners. And then last, validation of interpretations. It's hard to believe a important result if you didn't do at least just a small validation that your system is working in the setting that you're trying to do it in. So even if it's only a small proportion of your evaluation, anybody can poke holes in any of this research. And if you have some on-site contemporaneous validation, you've got an argument against the people who want to poke holes in the results of your research. And never discount serendipity. Sometimes that newspaper article comes out and says, yes, you nailed it. And that's such a great feeling. I don't have a pretty picture, but does anybody have questions? I ran a little bit over, but we started a little bit late. Actually, do you want to save it for panel?
No, we can go to